So this is just a quick supplement to work with section 3.4, 3.5, part 2. And this is the process of expanding polynomials. Once we have roots and have factors, we're going to now build the standard form polynomial by multiplying all our factors together. We're going to start with a couple basics here, and we're going to use and see how the difference of two squares can help us easily expand polynomials that have either complex or irrational roots. So some review. First things first, if x equals c is a root of a polynomial, then x minus c is a factor of that polynomial. 2, complex roots always come in conjugate pairs. A plus bi, a minus bi, 2 plus 3i, 2 minus 3i, whatever it might happen to be. And that same structure comes from irrational roots. They also will always come in conjugate pairs. 2 plus the square root of 6, 2 minus the square root of 6. And if we think about this going way back when in the time machines, these are natural conclusions that really come out of the quadratic formula. Think that through one more time. Natural extensions that always come out of the quadratic formula. Because what do we always think? What's buried in the middle of a quadratic formula? That plus or minus in the square root of b squared minus 4ac. So it's not a surprise that we see the plus or minus thing here working in terms of roots coming in pairs for irrational and complex roots. Then the last piece just to highlight is the difference of two squares. We talked about it numerous times. A plus b times a minus b gives us a squared minus b squared. Well, how does this turn out to be pretty valuable to us? Well, from the following. As I go to the next page, I won't cover things up, we'll just kind of talk. If 2 plus 3i is a root, then so is 2 minus 3i, just what we did on the prior page. How do I take those two different roots and write them in factored form? Subtract those root values, 2 plus 3i, 2 minus 3i. Subtract them both from x. So x minus, notice the parentheses here, 2 plus 3i. X minus 2 minus 3i must be factors of the polynomial because those are the roots. So with a little of algebra, just distribute the negative sign, and then I'm going to kind of get rid of my brackets and just work with one parentheses for a moment. What do I have as my factored form? X minus 2 minus 3i, x minus 2 plus 3i. So just look at how the factored forms resolve themselves. What do we do next? Well, if I'm going to be going to standard form, I'm going to be expanding these polynomials. I have to multiply these roots against each other. So here's what it's going to look like when we start up. X minus 2 minus 3i, x minus 2 plus 3i, just like I wrote on the prior page. Now look what I've done here. Same thing, I've gone back to some parentheses just to kind of help myself see it a little bit better. If I was so inclined, I could do the old brute force, distribute the x to these three terms, the negative 2 to these three terms, the negative 3i to these three terms. I'd wind up with 9 terms, and then I'd have to reconcile, consolidate, cancel out, so on and so forth. That's a lot of multiplication. But if I rewrite this way, look at what I see. X minus 2 shows up first, and then what do I notice? A minus 3i in one, a plus 3i in the other. And that's what I've reflected right here. I have x minus 2, that entity both times, minus 3i, entity plus 3i. And what do I get? I get the difference of two squares. This becomes nothing more than x minus 2 squared minus 3i squared. Remember again, this is my a minus b, a plus b. And here's my a squared. Here's my b squared. We should be real good at handling simple squares like this. X squared minus 4x plus 4. 3i, when I square it, I get 9i squared. I kept it in parentheses just to kind of belabor the point a little bit more. Minus what? 9i squared is 9 times negative 1 because I squared is negative 1. Minus a minus 9. X squared minus 4x plus 4 plus 9. Final result, x squared minus 4x plus 13. Again, I could have multiplied this out, gotten all these 9 terms up top, consolidated, simplified, eliminated, so on and so forth. I would have gotten to this right thing. This is a lot quicker. And that same process works very cleanly with irrational roots. I'm going to do an example that looks pretty doggone close. 2 plus the square root of 6 is a root. 2 minus the square root of 6 has to be a root. Here's what my factors forms looks like. X minus the first root, x minus the second root. No surprise. Same thing, distribute by negative sign. X minus 2 minus square root of x minus 2 plus square root of x. Do my cute reformatting because, again, this is a difference of two squares pattern. X minus 2, great. Minus square root of 6 plus square root of 6. Again, I am looking perfectly like the difference of two squares. And again, my a happens to be x minus 2, great. My b happens to be the square root of 6. Here we come down. Difference of two squares. There's my a squared, x minus 2 squared. Minus, there's my b squared, the square root of 6, taken to the second power. Again, x squared minus 4x plus 4, no surprise. Minus, what's the square root of 6 times the square root of 6? Good old 6. Can I simplify? X squared minus 4x minus 2. So again, something that would be pretty long to work my way out, cancel, consolidate, simplify, so on and so forth, has turned into a very, very simple process. You don't need to write out all these steps, obviously, but to see it, that's why it looks so kind of painstakingly long here and written out. But once you see that pattern, you can jump right into the difference of two squares, and you are home free for this.